Derivatives tell us how fast something is changing with respect to some variable. For example, the velocity of an object tells us how fast the object is moving with respect to time. The velocity of an object is the derivative of the object's position with respect to time. Similarly, the slope of the tangent line to the graph of a function f at x tells us how fast the y value of f is changing with respect to x. If the slope of the tangent line at x equals to a is large, then the graph is steep at x equals to a, and the y values are increasing fast with respect to x. So let's take a look at this graph here. Here we have the function f, and we have the blue tangent line at x equals to a. Now, this line here is very steep, since the slope of the tangent line is very large. If the slope of the tangent line at x equals to a is small, then the graph is not steep at x equals to a, and the y values are increasing slowly with respect to x. So here's an example. Here's our function f, and the blue tangent line at x equals to a. Here the slope is very low, the slope of the tangent line. So the function is increasing very slowly near x equals to a. Let's look at the slope of the tangent line to the graph of a function f at x equals to a. Okay, so here we have the graph of y equals to f of x. Here we have our point A. Okay, now first pick a point x close to A. Okay, so this is our x, and at x we have the y value f of x, and at A we have the y value f of A. Then find the slope of the secant line that connects this point with that point. Okay, so here's x f of x, and here's a f of a. Okay, now we want to find the slope of this straight line here that connects those 2 points. Okay, if we do that, we get f of x minus f of a divided by x minus a. This is by the slope formula. Okay, now as x approaches a, the slopes of the secant lines approach the slope of the tangent line. Okay, so let's take the limit as x approaches a of that expression right there. Okay, so that's the slope of the secant line, and we want to take the limit as x approaches a. We want to see what happens to that slope as x approaches a. Wherever it goes, whatever the limit is, that's the slope of the tangent line at a. Okay, let's say that the point x is a plus h for some small h. Then as x approaches a, h approaches 0. So substituting x equals to a plus h into the limit formula that we had, we get this. The limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, here's the graph. Here we have the function f, our point a, and then to the right of that we have a plus h, where h is some small number. Okay, and at a we have f of a for the y value, and at a plus h we have f of a plus h. Okay, now letting h go to 0 is the same as letting x approach a. So we can define the derivative of a function at x equals to a as this above limit here, this limit here. Okay, so f prime at a, the derivative of f at a, we can define that to be the limit as h approaches 0 of f of a plus h minus f of a all over h. The derivative tells us the rate at which f is changing with respect to x at the point A. An alternative definition is given by this limit. F prime at a equals to the limit as x approaches a of f of x minus f of a all over x minus a. Remember, this is the same as what we had earlier, the slope of the tangent line at x equals to a.